All right, in this video, I'm going to talk about section 10.3, which is Taylor series. So I'll do a couple examples where I actually find the Taylor series of a function. And then I want to look at finding new series from a table of known Taylor series. And finally, I'll finish up with a binomial series expansion example. All right, so first off, let's look for a Maclaurin series. So this function, ln of 1 plus x, is one of the classic Maclaurin series that's given in table 10.5. So this is in the table, but let's actually derive the Maclaurin series. So remember, the Maclaurin series is just the Taylor series, but centered at 0. So here, ln of 1 plus x can be written as an infinite series, k equals 0 to infinity, where the terms of the series are the kth derivative evaluated at 0 divided by k factorial times x to the k. So in these problems, if you're ever asked to find a Maclaurin series or a Taylor series, you have to find essentially what this coefficient looks like in terms of k. So you always start off with like k equals 0, right? Find the original function is ln of 1 plus x, and then plug in 0. So you get ln of 1 plus 0, which is ln of 1, which would be 0. Okay, so the first value is just 0. So at k equals 1, that means I do the derivative. The derivative of ln of 1 plus x would be 1 over 1 plus x. And so f prime of 0 would be 1 over 1 plus 0, which is 1. So I keep doing this, and then we have to divide these numbers by k factorial, so I'll do that in a second. But here, just continue on, right, and find the second derivative. So to find the second derivative of this, perhaps I'll write it as 1 plus x to the negative 1, so you know that this is negative 1 plus x, right, to the negative 2, which means f double prime of 0 would be negative 1 plus 0 to the negative 2, which again is negative 1. Continuing on, when k equals 3, we have the third derivative, which would be positive 2 times 1 plus x to the negative 3. So the third derivative at 0 would be, this should be a 1, would be 2 times 1 plus 0 to the negative 3, which is 2. Okay, so let's go one more. Now you'll notice that every time I do the derivative here, like there's going to be a factorial that comes out, correct? Because now I'm going to have to multiply this 3 by the 2 to get a 6. Also, you might be able to notice that, right, it's going to be an alternating series because of the negative sign. So here I'll get negative 6 times 1 plus x to the negative 4. So f to the fourth derivative at 0 would be negative 6 times 1 plus 0 to the negative 4, which is negative 6. Okay, so what I want to notice, what I wanted to show you here is that 0 is just 0. 1 is 0 factorial, right? This is negative 1 factorial. This is positive 2 factorial. And this is negative 3 factorial. So here's the pattern. So it seems like when k is 1, I got 0 factorial. When k is 2, I got negative 1 factorial. So we might be able to establish that the kth derivative at 0, right, is an alternating sequence. And that would be k, let's see, plus 1 and times k minus 1 factorial. So as a sanity check, you can check to see, right? Don't even worry about k equals 0 because I get 0 back. So let's start at 1. So when k is 1, I will get negative 1 squared, which is positive, and then 1 minus 1 factorial. So you get 0 factorial. So what does this mean? Well, f to the k, right, to the 0, the kth derivative at 0 divided by k factorial, that's negative 1 to the k plus 1 times k minus 1 factorial, all divided by k factorial. So we get negative 1 to the k plus 1, simply divided by k, since the k factorials and k minus 1 factorial cancels out. So this means ln of 1 plus x, right, is equal to the infinite series k equals 1 to infinity. Notice I'm starting at 1 because the 0 term was just 0. And so we get negative 1 to the k plus 1 over k times x to the k. So that would be the Maclaurin series for ln of 1 plus x. All right, then we can do a Taylor series for a function that's not centered at 0. So in this case, f of x, right, 2 to the x, can be written as an infinite series k equals 0 to infinity of the kth derivative at a, in this case, which is 1 over k factorial times x minus a to the k. So updating this, I'll plug in the value for a. This would be 0 to infinity, the kth derivative at 1 over k factorial times x minus 1 to the k. So in reality, what I need to figure out is, right, is there a pattern for f to the k, the kth derivative at 1? So the same old thing. So when k equals 0, right, I just get f of x equals 2 to the x. So f of 1 would be 2. When k equals 1, now what's the derivative of this? Well, it's ln of 2, right, times 2 to the x. So f prime of 1 would be ln of 2 times 2. So when k equals 2, I would get f double prime of x would equal ln of 2 squared times 2 to the x. And so the second derivative at 1 would be ln of 2 squared times 2. So this one's not as bad. I know that every time I do the derivative, right, an ln of 2 is going to pop out. So we might be able to deduce that, right, the kth derivative at 1 is simply going to be ln of 2 raised to the k power, and then that times 2. Which means the kth derivative at 1 divided by k factorial, right, is simply going to be ln of 2 to the k times 2 all over k factorial. Which means 2 to the x can be written as the series k equals 0 to infinity of ln, I'm going to write the power right there, to the k, ln to the k power over 2 to k factorial times x minus 1 to the k. So that is a Taylor series not centered at 0. So how can we use these things? Well, check out this function. I'm going to use the table 10.5, but I'm going to recall that, right, we just figured out that the series for ln of 1 plus x is given by negative 1 to the k plus 1 over k times x to the k. So in that one theorem that we discussed in class, right, if I'm trying to find the series for ln of 1 plus 2x, wherever I see an x in this series right here, I can replace it with a 2x. So this means ln of 1 plus 2x can be written as the series k equals 1 to infinity. Sorry, k equals 1. A negative 1 to the k plus 1 times 2x to the k all over k. And so reducing this a little bit, I can write this as negative 1 to the k plus 1, 2 to the k, x to the k all over k. So this is my new series for that function. So looking at the table, this one's a little bit more complicated. There's an x out front and there's an x squared here. But looking at the table, there is a function for arctan, which is given by k equals 0 to infinity of negative 1 to the k times x to the 2k plus 1 all over simply 2k plus 1. All right, so we use this base identity here. And first, let me figure out a series for arctan of x squared. Notice wherever I see an x in this series, I'm just going to put an x squared. So I get negative 1 to the k, x squared to the 2k plus 1. To the 2k plus 1. So simplifying this, right? Multiplying exponents, I get x to the 4k plus 2 all over 2k plus 1. Now finally, if that's arctan of x squared, all I have to do is multiply by an x outside. So that means multiplying by an x outside of the series. And I can bring that x directly inside and add it to these exponents here. So x arctan of x squared is equal to the sum of k equals 0 to infinity of negative 1 to the k, x to the 4k plus 3 over 2k plus 1. So that's how I would represent that function there. All right, last example is a binomial series example. So here it's kind of tough to generalize a binomial series, so I might ask something like, find the first 4 non-zero terms of this series. So what you have to look at is, right, 1 plus x to the p, and if I go back to this function here, this is 1 plus x to the 1/2, right? So the general formula here is k equals 0 to infinity of p choose k, x to the k. All right? So this function is kind of weird, but I'll show you how it works. So if I wanted to do 1 plus x to the 1/2, right, the first term would be 1/2 choose 0, x to the 0, plus 1/2 choose 1, x to the 1, plus 1/2 choose 2, x squared, plus 1/2 choose 3, x cubed. Okay? So I have to figure out essentially these 4 coefficients, and I'm pretty much done. Now, it turns out that p to the 0 for any p is always equal to 1. So it doesn't matter. If I'm choosing 0, that first coefficient is always 1. So 1/2 choose 0 is 1. So 1/2 choose 1. What is that defined as? By definition, this says to take 1/2, multiply it by the number that's exactly 1 less than it. So I'm subtracting 1. So 1/2 minus 1 is negative 1, over 1 factorial. Okay, that's it. So this would be negative 1/4. So this is 1, this is negative 1/4. 1/2 choose 2. This says do 1/2 times the one number below it, and then times the number below that, and then stop. So we have 2 factorial. Okay, so that would be 1/2 times negative 1/2, right, times negative 3/2, all over 2. So this would give me 3/16. Finally, 1/2 choose 3 is 1/2 times negative 1/2 times negative 3/2 times negative 5/2, all over 3 factorial. So this gives me, this would be, let's see, that's for the 3 factorial. Then I have 1/2, negative 1/2, negative 3/2, and negative 5/2. Okay, so we get, let's see, a 15, negative 15 up top, and a 6 times 16 in the bottom. I don't know. 96. So this is, which probably is divisible by 3, so we get negative 5 over 32. Okay, so the square root of 1 plus x can be rewritten as 1 minus 1/4 x plus 3 over 16 x squared minus 5 over 32 x cubed plus blah, blah, blah. So those are the first 4 non-zero terms of that series.